let's talk about the different relationships in a scatter diagram and then the linear correlation coefficient. So here you'll see some different pictures of some scatter plots that represent either linear relationships or nonlinear. So here we'll see two relationships. So here we have the positive linear relation and then a negative linear relation. We're talking about linear relation and we're talking about the relationship. The positive one is where we have a positive slope and a negative one is where we have a negative slope. So as the explanatory variable increases, the response variable also increases is when we have a positive linear relation. And then as the explanatory variable increases, the response variable decreases is where we have a negative linear relation. And then you'll see some examples here of nonlinear. So here we have a relationship between the explanatory and response variables, but it's nonlinear. Same case here, and then here we have one that there's no relation at all. So we say that, so I just talked about that. So positively associated when one goes up, the other goes up. Negative is when one goes up, the other goes down. And then our linear correlation coefficient measures the strength and direction of the linear relationship between two quantitative variables. And then we use R to represent that. And then the Greek letter rho there represents the population correlation coefficient, and we're not going to talk about that. We're only going to look at the sample. So some properties of the linear correlation coefficient is that it's between -1 and 1 inclusive. So when we say inclusive, we mean that those endpoints are included there, so it can be -1 and 1. So if R is +1, then a perfect positive linear relationship exists. And if it's -1, then a perfect negative linear relation exists. The closer it is to +1, the stronger the evidence of positive association is between the two variables. And similarly, we have that the closer it is to -1, the stronger the evidence of a negative association. If R is close to 0, then little or no evidence exists of a linear relationship. Just because R is close to 0 doesn't imply that there's no relationship, just no linear relationship. Again, R is measuring the linear relation between the variables. It is unitless and it is non-resistant. So if you go back and think about how we were talking about mean and median and which one was resistant back in chapter 3, then you can think about it that way. And then there, so you can see some different values. So here's when we have 1, so a perfect straight line there. Here's one with about 0.9, so it's pretty strong. There's a couple values kind of off of that. And then here's one with 0.4, so not as strong. So negative, so a negative slope, perfect straight line there, and then one that kind of varies off, and then one that kind of spreads out there. And then here's some with no relation. So now if we want to test for a linear relation, we want to look at the absolute value of the correlation coefficient and then find the critical value in the table and then compare the absolute value of the correlation coefficient. And if it's greater than the critical value, then we can say a linear relation exists. If R is positive, then there's a positive linear correlation. If R is negative, then there's a negative linear correlation. And the reason we look at the absolute value of the correlation coefficient is because the critical values are always positive, and that way we can have a fair comparison. And table 2 from appendix A looks like the following. So you'll see there that those are all positive, and that's not the whole table, it's simply a screenshot of the table. So that's why we're comparing that. So that's the linear correlation coefficient.